5B, the addition rule and the rule of the complements. Okay, so previously we talked about theoretical probability and classical probability, experimental and empirical probability, right? Dealing with single things happening. The probability that event A occurs is this. And we found it either theoretically or experimentally. Now we're going to talk about a compound event. Compound means multiple things happening. So when we're dealing with a compound event, you're talking about an event formed by combining two or more events. A good example is OR. The probability that either event A or event B occurs. So what that means is, we'll be happy if event A occurs, we'll be happy if event B occurs, we'll be happy if both of them occur. We're just looking for at least one of them to occur. So we're saying the probability that A occurs, or B occurs, or both occur, right? So that's what we're looking at. Probability that one, the other, or both of them occur. So to start with that, we're going to deal with contingency table. Contingency table is kind of like dealing with finding the probability from a population, right? When we have our frequency distribution, we say, what's the probability that such and such occurs? Well, now a contingency table, since we're dealing with multiple events, we're actually going to build a table that's more two-dimensional, as opposed to just this thing happening, one column. So let's say I'm looking at students and instructors. And males and females. So I have two variables involved here. I have status at the school, a student or instructor, or status in the classroom, student or instructor, and gender. So now I've got these two things. Well, first I need to take some data. So let's get some data. 245 male students, 17 male instructors, 268 female students, 14 female instructors. Okay, so this is called a contingency table right there. It gives you both of your variables and says the number of occurrences for each of these intersections of those. Male students, or students that are male, students that are female, instructors that are male, instructors that are female. So one of the first things we want to do when we're dealing with a contingency table is we want to sum things up. How many males do we have? We have 245 male students plus another 17 male instructors, 262. So we have 262 males. How many females? 268 female students plus another 14 female instructors, 282 females. Excuse me. Let's also sum across 245 male students plus another 268 female students. That's 513 students. 17 male instructors plus another 14 female instructors. That's 31. instructors. And then our final summation that we're going to do here is we're going to add up how many students plus how many instructors, which is going to tell us how many total. We have 513 students plus another 31 instructors. That's 544 people in our sample. Notice also 262 plus 282 gives us 544. Avoid the classic mistake. You are always going to either add up a row or add up a column. Don't add up both at the same time. Classic mistake, people add this up and they add that up and get 1,088 instead of getting 544. These will add up to the same amount as long as you did everything correctly. Now, we can now use this table to answer some basic questions for us. What is the probability that we select a female? Probability that we select a female. Well, how many females are there? There are 282 females out of 544 people. Now remember, if you're going to keep that as a fraction, you have to reduce that. Or if you're going to turn it into a decimal, I get 0.52. What's the probability that we select a male student? Probability we select someone who's male and a student. Right, if they're a male student, they're both male and a student. Well, we have 245 male students out of 544. We turn that into a decimal, that's about 0.45. What about the probability that we select a female or an instructor? Female or instructor. Well, let's see, this is where it gets a little more complicated. The probability that we select a female, well, these are females, these are females, okay? How about instructors? Those are instructors, right? So we have 268 plus 14 gives me 282, plus 17 gives me 299, over a total of 544, which gives me about 0.55. The probability that we select a female or an instructor. So contingency tables are great because it's really easy to pull information out of here. What's the probability that we select a female student? 268 out of 544. What's the probability that we select an instructor? 31 out of 544. Very easy to pull these things out of a contingency table. Let me get rid of my little circles here. Okay, and what I'm going to do is I'm going to move those over here, just to give myself some. So, probability of female was about 0.52. Probability of male and student was 0.45. Probability of female or instructor, 0.55. Okay, that's going to allow me to get this out of the way here. Remove all that. Just going to give myself a little more space to work with. And I'm going to get this out of the way just a little bit. And we're going to talk about the general addition rule. Right? The addition rule, right? The general addition rule, which says the probability that event A or B occurs is equal to the probability that event A occurs plus the probability that event B occurs minus the probability that both event A and B occur. Okay, so the probability that either A or B occurs is equal to the probability that event A occurs plus the probability that event B occurs minus the probability that they both occur. Okay, well that sounds good. So what's that telling us? Well, let's look at this. We had a probability that we selected a female or an instructor. Probability that we select a female or an instructor. Now what we did was we found all the ones that fit that, we added them all up and divided by the total amount. Now what I'm going to do is I'm going to use this rule. Well, what's the probability that we select a female? So that's equal to, I should say, the probability that we select a female plus the probability that we select an instructor minus the probability that we select a female who is an instructor, F and I. What's the probability that we select a female? There are 282 females out of 544. What's the probability that we select an instructor? There are 31 instructors out of 544. What's the probability that we select a female instructor? There are 14 female instructors out of 544. So what's the probability that we select a female or an instructor? I don't need that over there. Okay. Common denominator, so 282 plus 31 gives me 313 minus 14 gives me 299 or 544 or 0.55. Well, look, it worked. That's what we got before. We got 299 over 544, which came out to be about 0.55. The probability that event A or event B occurs. Now you may ask, because it makes sense, okay, we're looking for this or that to occur, so hey, it's the probability of the first one plus the probability of the second one. You may be asking, what's with this probability, subtracting out the probability that both A and B occur? Well, let me show it to you this way. The probability that a female is chosen, all of those are females. Probability that an instructor is chosen, all of those are instructors. Now, it should be obvious to you at this point that those 14 individuals were counted as females and counted as instructors. They were counted twice. Well, what are those 14 individuals? Those are the female instructors, those that are both female and instructors, or the probability of A and B occurring. So what we're doing is we're subtracting out the duplication. If we find the probability of females, we included this group. If we find the probability of instructors, we included this group. So by including them twice, we need to get rid of them once, and that's why we subtract. Now you may look at this and go, Mr. Davis, that's great, that's wonderful. Why do I want to go through all this when I could just add up these three and divide by 544? And that's a great question. And the great answer is because you don't always have a contingency table. What if I just know that the probability of selecting a female is 0.67, the probability of selecting an instructor is 0.19, and the probability that I select a female instructor is equal to 0.15. And I want to know what's the probability that I select either a female or an instructor. If that's the case, now I'm stuck with this because I don't have a contingency table. Now, I could be tricky and I could kind of create one. Because if I said, hey, what if I pretend like I have 100 people and 67% of them are female, that I could come out with a total, I could come out with 67 of them being female at the bottom of the table. I could come out with 19 of them being instructors, a total of 100, which means I could determine how many were male. I could determine how many were students, and I could kind of backfill. But you want to talk about wasting a lot of time doing a lot of work you don't have to. That's it right there. So how do I do this? I just plug it in. The probability of being a female is 0.67. Probability of being an instructor is 0.19, minus the probability that they're both a female and instructor, or a female instructor, which is 0.15. 0.67 plus 0.19 gives me 0.86 minus 0.15, 0.71. So the probability that I select a female or an instructor is 0.71. So there we go. So that's pretty straightforward with that. We just have to remember that we're going to add together the probability of either one occurring, then we need to subtract out the probability that they both occur. So that's a good start. Well, why do we have to deal with that? Well, I already showed you this duplication. Well, there is a situation where we don't have to deal with that. And that's when we're dealing with mutually exclusive events. So mutually exclusive events. Two events or more events are considered to be mutually exclusive if the occurrence of one makes the occurrence of the other one impossible. So they're mutually exclusive. If one occurs, the other one cannot happen. Let's say event A is we roll an odd number. Event B is that we roll a 2. So we've got two events, rolling an odd number and rolling a 2. If I roll a die once, can both event A and B occur at the same time? Well, 2 is not an odd number. So therefore, these events are mutually exclusive. If I roll a known odd number, there's no way I could have rolled a 2. If I rolled a 2, there's no way I could roll an odd number. So those are considered to be mutually exclusive events. In the case of mutually exclusive events, the general addition rule just turns into the addition rule for mutually exclusive events, that the probability that event A or B occurs is equal to the probability that event A occurs plus the probability that event B occurs. Because if I find the probability that they both occurred, they can't occur at the same time since they're mutually exclusive, so that probability would be 0. So you can call this a special case of your general addition rule, where the probability of event A and B occurring at the same time is 0. It will never happen. Okay? This can be expanded out into multiple events too. I could have the probability that A or B or C or D or E, etc., is equal to the probability of A plus the probability of B plus the probability of C plus the probability of D plus the probability of E, etc., etc., etc. So let's look at one of these. I'm just going to move this equation up here quickly. So the probability that A or B occurs for mutually exclusive events is equal to the probability that event A occurs plus the probability that event B occurs. Okay, so I'm going to take a quick moment to introduce you to playing cards. Now, I'm not going to show you any at this point, but I'm just going to explain the breakdown of playing cards. So first of all, if you're dealing with a standard deck of playing cards like you'd use for poker or such, there are 52 cards in the deck. That is not including the jokers. There are 52 cards. There are 4 suits. Those suits are very poorly drawn. Spades, clubs, diamonds, and hearts. And they are those colors. So spades and clubs are black, diamonds and hearts are red. 4 suits. There are 13 cards per suit. Per suit. Those are the numbers 2 through 10, Jack, Queen, King, and Ace. So numbers 2 through 10, Jack, Queen, King, and Ace. Jack, Queen, King are all face cards. Face cards because they are people and they show a face of a person on them. So the Jack, the Queen, and the King. So 13 cards per suit, numbers 2 through 10, Jack, Queen, King, and Ace. Now yes, Ace many times gets used as a 1, but it is not a number of cards. So you've got number cards, face cards, and the Ace. Okay? I introduce you to this because for probability, cards work great. They make it very easy to show a number of things. So now that I've given you that, let's find the probability that you pull either a 2 or a face card from a deck of cards. So I need to know the probability of pulling a 2. There are 4 suits, and each of those suits has a number 2. So there are 4 2s in the deck out of the 52 cards in the deck. probability of pulling a face card, there are 3 face cards per suit. Jack, Queen, and King, there are 4 suits. 3 times 4 is 12, so there are 12 face cards in the deck out of the 52 cards in the deck. Now, a 2 cannot be a face card, and a face card cannot be a 2, therefore these events are mutually exclusive. So therefore the probability of pulling a 2 or a face card is equal to the probability of pulling a 2 plus the probability of pulling a face card, which is equal to 4 over 52 plus 12 over 52, which gives you 16 over 52. If I divide top and bottom by 4, I get 4 over 13, or if I want to put that as a decimal, that is approximately 0.31. And that is the probability that we select either a 2 or a face card, because these are mutually exclusive events. Okay, so that's dealing with the addition rule, either the general addition rule, which is when the events can occur at the same time, or the addition rule for mutually exclusive events, which is when they can't occur at the same time. Last thing I'd like to talk about is the rule of complements. Now, some of you are experts at the rule of complements. You always make sure that other people know that they're appreciated. You tell them how wonderful they are. And so, no, wrong rule, okay? Rule of complements, not compliments, complements. If you've ever heard someone say they really complement each other, talking about 2 people who are spending time together, right? They really complement. It means the one fills in for the lacks of the other one, and therefore they go together well. I find that my wife and I are very good complements to one another, because where I'm strong, she's weak. Where she's strong, I'm weak. Or I should say the other way, where I'm weak, she's strong. Where she's weak, I'm strong. It sounds a little better to say that the other person's strong where you're weak, as opposed to saying the other person's weak where you're strong, right? So they complement each other. They go together well. And when you're talking about complements, you're talking about everything else. So if I have the probability of event A occurring, event A is here. If I say the probability of A prime is the complement of event A. So the complement of event A. It could also be written as the probability of A to the C, where that is the complement of event A. And the complement is everything else. It's what A is not. So the probability of the complement of event A occurring, or the probability of the complement of event A occurring, is equal to 1 minus the probability that the event itself occurs. If I have event A, in fact, let me switch that to event B. So let's say I say event B is that I roll a 3. Then event B complement is that I do not roll a 3. So it's that I don't roll a 3. So that's all it is. If the event is flipping a coin and getting heads, then the complement is that I do not get heads. Now be careful with that, because a tendency that people have is they think, well, okay, if you don't get heads, then you got tails, so they say the complement is getting tails. And although that may seem to make sense, that's not how we define the complement. We define it as not having the event occur. So if we say the probability, if we have event A is flipping a coin and getting heads, then event B is not getting a heads. It's kind of like the other category when we're dealing with categorical data, that we do it as a catch-all. You don't have to worry about missing a possibility. In reality, couldn't you say with flipping the coin that there's also a possibility that it lands on edge? So if the probability of getting heads is 0.5, then the probability of not getting heads is 0.5, right? It's the other half of it. But there's always the possibility that it could land on edge. So it's not just the probability of getting heads, and then the complement being the probability of getting tails. The probability of getting heads is the event. The probability of not getting heads is the complement. Now, I said it's 1 minus the probability of event A. Well, that's pretty straightforward, that the probability that something will always occur is 1. Now, it should make sense to you that if I want to find the probability that something occurs or it doesn't occur, doesn't that mean it's got to be 1? Because either it's going to occur or it's not going to occur. One of them has to happen, so the probability that either the one or the other occurs is 1. So if we want to find the probability that the complement occurs, we subtract the probability that the event occurs from 1. So let's put that in place. I'm going to leave that right here just so we see that. So the probability that the complement of event A occurs is equal to the probability that 1 minus the probability that event A occurs. Okay. The probability that I randomly select a truck from the parking lot is 0.12. What's the probability that I do not select a truck? Well, that's equal to 1 minus the probability that I select a truck, which is equal to 1 minus 0.12, which is equal to 0.88. And that is the rule of complements. If we know the probability that an event occurs, then subtract that from 1 and you have the probability that the event does not occur. The probability that this lecture will end in the next minute and a half is 0.99. The probability that the lecture does not end is equal to 1 minus 0.99 or 0.01. And thus, the lecture ends.